Hello and welcome to another exciting lecture for stats. In this lecture, we will be talking about everybody's favorite topic, probability. So this is the probability lecture that is the 1-week probability lecture. As I said earlier in the semester, I do probability different in different classes. Sometimes it's 2 weeks, sometimes it's 3 weeks, sometimes it's 1 week. You guys get the 1 week of probability. However, that means the lecture is a little bit longer. There's a little bit more in it because I want to make sure everything that's important gets put into the lecture. So what are our learning objectives for this lecture? First, we've got a very simple one, just define probabilities. So that's learning objective 1. Then we get learning objective 2. We're going to define something again. So we're still on the topic of basically defining the rules or the basic overview of the topic. So we're going to define sample space and events. Then we're going to define complement of an event and the properties of an event and its complement. After that, we will get into the calculations. So we'll start calculating. So these first three, define, then we're going to start calculating. Calculate the marginal, joint, and conditional properties. Calculate the union of events using the addition rule with and without mutually exclusive events. We'll calculate the intersection of events with and without replacement. We'll calculate the probability of at least one, which is a special case. Then we'll calculate the probability of a specified number of outcomes occurring using the binomial probability distribution. And then we'll finish up with an overview of some of the other probability distributions, the ones we're not going to learn how to calculate in here. So you don't have to worry about the calculations. I'll show you the formula for them, but we're not gonna give examples. It's not something I'm gonna put in the homework or the exams. It's more of just a, hey, these are the other probability distributions that are out there besides the binomial. So we'll look at hypogeometric, Poisson, exponential, probability distributions, and then finish with Bayes' theorem. So before we get into some of the hard stuff, some of the complex stuff, some of the different types of things, let's start with the easy. Let's start with defining probability. So a couple definitions. We'll start with defining probability. Probability is just the likelihood of an event occurring. So if I'm asking what the probability of something occurring is, I'm asking for the likelihood of that event occurring. We're going to write it a few different ways, but the typical way you're going to see it is a P with and then a letter in parentheses. That's just the probability of the event that's in the parentheses occurring. So P with an A is the probability of event A occurring. P with a B, probability of event B occurring. And it can be many different things that you can have in the parentheses there, but it's basically you're saying the probability of that event happening. Probability is always going to range from 0 to 1. So this is something we talked about recently in the correlation stuff, but it ranges from 0 to 1 with a closer to 0, meaning a less likelihood of the event occurring, closer to 1, meaning an increased likelihood or a greater likelihood of an event occurring. So something that's 0 means there's 0 probability or 0 chance of it occurring. Something that's 1 means there's 100% chance of the event occurring. And we're generally going to express probability as either a proportion or as a fraction. We're almost always going to do it this way in here. You're going to see it this way. I prefer, even if you get fractions, that you convert them to proportions. So if you get a 1/6, convert it to a proportion after that. Something like that. And then we get into the next definition here, and that's defining sample space in the events. So sample space specifically is going to be all possible outcomes. So let's say you are talking about the probability of rolling a 1 on a d6 on a die. Well, all possible outcomes, the sample space is going to be 1, 2, 3, 4, 5, or 6, because that's all possible outcomes. A coin is an easy one. There's 2 possible outcomes, heads and tails, if we're talking about a normal coin. A standard deck of playing cards without the jokers in it is going to have 52 cards in it. So there's 52 possible outcomes. And I'll actually use this in an example quite a bit. So let me explain it real quick. Most of you have probably played with playing cards before, but some of you haven't. So there are 52 cards. There are 26 red, 26 black. Within that, I don't have room to go down, but within that 26 red, there are 13 hearts and 13 diamonds. And within the black, there's 13 spades and 13 clubs. And those 13 are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So that is the makeup of a standard deck of playing cards. I use this as an example quite often when I'm doing probability examples, so I explain it a little bit here, even though I am always running under the hope that everybody has played with decks of cards before, but I never assume that everyone has played with decks of cards before. So that is the sample space. And if we talk about the sample space and an event is going to be an outcome or set of outcomes in the sample space of interest. So it is what is of interest. So what do I mean by that? Let's say I talked about before, I said rolling a 1 on a d6. So there's 6 possible outcomes. The sample space is 1 through 6. The event is a 1. But I could even do it as a set of outcomes. So I could say an even number. So in that case, a 2, a 4, or a 6 would be my events. Even though the sample space would be 1, 2, 3, 4, 5, and 6. So the sample space is all possible outcomes. The event is the outcome of interest. So in this case, if the outcome of interest is an even number, 2, 4, and 6 are the even numbers that would be the events. And as long as we're still defining things, we're now going to define the complement of an event. So we just explained an event. So what is the complement of an event? You're going to see the complement of an event written many different ways. You might see it as not A. That's the way I'll say it out loud, is not A. I'll either say the complement or I'll say not A. You can also see it as the letter with a bar over it. So this doesn't mean mean. Don't confuse it with the mean. That's one of the things that can be difficult, is we're using same symbol to mean multiple different things. But typically, if we're talking about it like this, how you're going to see it is the probability of not A. So the probability of A with a bar, that would mean the probability of not getting A. Another way you can see it is with the squiggle A. And in a sense, what a complement is all outcomes in our sample space that are not in the event. So I gave the example on the previous slide of a D6, which has the sample space of 1, 2, 3, 4, 5, and 6. The event that we were looking at was the probability of getting an even. If we're looking at the probability of getting an even, we're looking at, in that event of even, it is a 2, a 4, and a 6. So the probability of getting, and I'm going to erase the A here, we'll go back and do a not even. The probability of not even would be what would be the outcomes would be 1, 3, and 5, because those are all the outcomes that are not even. So it's either even or not even. How about, let's say we said drawing a card from a standard deck, if the event is a jack, so any of the 4 jacks, the event is a jack, then the complement is any card that's not a jack. So this would be jack, and then the complement would be not jack, or not jack, or squiggle jack. You're going to see me almost always write it like this, but say not jack. It should be noted that if you add up the probability of an event plus the probability of the not event, so if you add up the probability of an event plus its complement, it's always going to equal 1. That is because there's no overlap. They're mutually exclusive. What do I mean by that? Meaning there's no cases where it's both an event and a complement. You can't have the probability of drawing a jack and then say its complements is going to be jacks as well. No, its complement is anything that's not a jack and everything that's not a jack. So if you take and look at all possible examples, they're either going to be in the event or going to be in the complement of the event. The example let's look up here, when we were looking at rolling that die, there's 6 total outcomes. In this case, since we're looking at the event being evens, 3 of the 6 are in evens, the other 3 of the 6 are in not evens. So that is the complement of an event. I did just mention what mutually exclusive is, but what does mutually exclusive fully define? Mutually exclusive is when events do not have any outcomes in common. There's no overlap. So if I was looking at the probability of evens and the probability of odds on a die roll, those are mutually exclusive because they have no events in common. There is no instances where a die roll is both an even and an odd. It is either an even, which is a 2, a 4, or a 6, or an odd, a 1, a 3, or a 5. Example index of cards, spades and hearts are mutually exclusive. There are no cards that are both spades and hearts. But kings and clubs are not mutually exclusive. They are not mutually exclusive because the king of clubs, it falls in both groups. If we were looking at the probability of kings and the probability of clubs, the king of clubs is in both groups, so it's not mutually exclusive. Thing here, though, and this is one of these things, follow along with this, because what are the properties of an event and its complement? Here's the first of those properties. An event and its complement are always mutually exclusive. So we're going to look at these properties of an event and its complement. The first of those properties is that an event and its complement are always mutually exclusive. Let's look at a visual representation of an event and its complement. First, you've got A, whatever it is we're looking for. Then you've got B, whatever it is we're looking for. There is no overlap. There's nothing that are in both groups, so these are mutually exclusive. However, if we're looking at A and B, where there is a section that's both A and B, those are not mutually exclusive. Let's look at another term now, exhaustive. So what are exhaustive events? Exhaustive events are events that contain all outcomes in the sample space. So let's say I was talking about evens and odds. So evens are 2, 4, and 6. Odds are 1, 3, and 5. If you have both evens and odds, they are exhaustive because all possible outcomes are accounted for in either evens or odds. However, if I was looking for, let's say instead, I was looking for evens and low numbers. So evens are 2, 4, and 6, and low numbers are 1, 2, and 3. This is not exhaustive because what's missing? The 5. The 5 is not accounted for. 1, 2, 3, 4, and 6 are accounted for, but the 5 is missing. So in this case, they are, in this up here, they're exhaustive. Down here, they are not exhaustive. They're also not mutually exclusive because the 2 is in both groups. So they're not exhaustive or mutually exclusive. Example here, red cards and black cards are exhaustive because you've got the 26 red cards, you've got the 26 black cards. There's no overlap. They're mutually exclusive, so all 52 cards are accounted for. So they are exhaustive. However, hearts and clubs are not exhaustive because there's 13 hearts and 13 clubs. Now we've only accounted for 26 of the 52 cards. If we said hearts, clubs, diamonds, and spades, those 4, then it's exhaustive because it's used them all up. There doesn't only have to be 2 events that we're looking at. We could only be looking at 1 event. We could be looking at 2 events like we are with red and black or with hearts and clubs. We could be looking at 4 events though. Hearts, clubs, diamonds, spades, we're looking at 4 events. And then in that case, they would be exhaustive because they use up all of the possibilities. Let's look at number 2 for properties of an event and its complement. An event and its complement are always exhaustive. So an event 1 was an event and its complement are always mutually exclusive. 2, an event and its complement are always exhaustive. Let's look at a partition now. We're still on these definitions. A partition is an event when events that are mutually exclusive and exhaustive, they form what's called a partition of the sample space. So, my example that I just gave a minute ago, let's actually look at the evens and odds first. You've got evens and odds, 2, 4, and 6, 1, 3, and 5. These are mutually exclusive and they're exhaustive, so these together form a partition of the sample space. However, if we looked at evens and low numbers, 2, 4, and 6, 1, 2, and 3, they are not mutually exclusive, they're not exhaustive, and they do not form a partition. Some examples here: diamonds, hearts, spades, and clubs. If you put all 4 of them together, they're mutually exclusive. There's no overlap in any of those groups. There is no diamonds that are also hearts, spades that are also hearts, spades that are also clubs. There's just no overlap there. So they are mutually exclusive, and all possible cards or outcomes are accounted for because there's 13 diamonds, 13 hearts, 13 spades, and 13 clubs. So they are mutually exclusive, they are exhaustive, so they form a partition. Probabilities of events that form a partition must add up to 1, just like an event and its complement do. And finally, this is our third for properties of an event and its complement. An event and its complement always form a partition. So an event and its complement, they are mutually exclusive, they are exhaustive, and they always form a partition. That is the 3 properties of an event and its complement. So let's get to the computation side of things. So the first thing to concern ourselves with is how do we calculate the probability of an event? Well, it's very basic, easy formula. The probability of an event equals the number of outcomes in the event divided by the total number of outcomes. So just the number in the event, the n of the event, divided by the n, big N here, indicates the total number of outcomes. Example. Let's say we randomly select a card from a standard deck of 52 cards. What's the probability of selecting a club? Let you think about that for a minute. What's the probability of selecting a club here out of a deck of 52 cards? Well, first off, I'll remind you there are 13 clubs. So if the probability of getting a club is equal to, and again, all basic probabilities like this are the number of the event divided by the number total. So the number in the event is 13. The number total is 52 because there's 52 cards, which is equal to 0.25. 13 divided by 52 is 1/4 or 0.25. So the probability of drawing a club when selecting one card out of a deck is 0.25 or 25%. You'll hear me quite often convert a probability into a percentage. You just convert a probability to a percentage by multiplying by 100, just like when we took those like relative frequencies and converted them to percents. You just multiply by 100. So we multiply by a probability by 100 to get a percentage. So the probability of getting a club when you draw one card out is 0.25 or 25%. This is the example we're going to use for this specific thing here. We're going to look at the probability of getting discrete variables. And we're going to create what's called a both a frequency distribution and a probability or a joint probability distribution. So this is the frequency distributions we did earlier in the semester, we did when you just have one variable. So that was just if you had that one variable, you had each of the quantities for that one variable, and you did proportions, you did basically frequencies for them, you did relative frequencies, you did percent. We are going to now do a frequency distribution table when you've got two variables. In this case, we've got self-esteem, which can take on a quality of low or high, and we've got depression that can take on a quality of low or high. Now, usually when you do these types of tables, you're not going to have more than 3 or 4 dimensions on each, or more than 3 or 4 levels on each. So again, self-esteem, you've got low or high. You could have low, mid, and high, but the whole point of this type of table is you need two variables that have at least 2 levels. And when you see here, some important things to note. So the grand total is, which is n, is 800. There were 800 individuals. We look up here, we see 800 individuals. So that bottom right is the grand total. That's our total n. So when we do all of those divisions by n, which is our total, that's what we're going to typically be dividing by. And then if we looked at just depression, so when we're looking at just depression, we come all the way over here to these two values. We're just looking at depression, we're ignoring self-esteem. 600 people have low depression, 200 people have high depression. Then if we just looked at self-esteem, ignoring depression, we note that 300 had low self-esteem and 500 had high self-esteem. Low depression and high depression. We've got low depression and high depression, low self-esteem and high self-esteem. That is the variables by themselves. Then of interest as well is these joint frequencies. What do I mean by that? I mean this 110 that we've got here is a joint frequency. You'll recall a frequency is a count, just a count. So the joint frequency of low self-esteem and low depression. So low self-esteem and low depression. 110 people had low self-esteem and low depression. You could look at this 490 here. That's 490 had high self-esteem and low depression. 190 had low self-esteem and high depression. And 10 had both high self-esteem and high depression. So that's how you read this table. But now let's look at this, the first learning objective of calculate both a marginal, a joint, and a conditional probability. So let's look at the marginal first. A marginal probability, also called a simple or basic probability, is the basic unit of probability that we have out there. It is the unit of probability when you're talking about the margins. So on that previous chart, we had what was in the center of the table, and we had what was in around it in the margins. So a marginal probability or a simple or basic probability is the ones we've been calculating so far. It's when you've only got one variable. It's the probability of an event that does not involve other events. So in the previous slide, you'll recall we had high and low self-esteem, high and low depression. Both of those, well, we had self-esteem and depression as our two variables that we're interested in. A marginal probability only concerns itself with one of the variables. It ignores the other variable. So you recall when I was talking about it, I was talking about how like 600 had low depression, 200 had high depression, ignoring self-esteem. Well, when we do the marginal probability, we're also going to be looking at that. We're going to be looking at just that marginal, just the probability of low depression or high depression, ignoring self-esteem. So other events are present, but they may be ignored. And this is that basic formula that I showed a couple slides ago. It's just the number in our event divided by the number total. Going back to that chart, let's look at these now. So again, recall our number total is 800. So our n equals 800. So in all of these cases, we're going to be dividing by that because remember, probability equals the number of in the event divided by the big N, the number total. So in this case, all of these, we're going to be doing a division. We're going to be dividing the number in the event by the grand total, but the grand total is the same for all of these. It is 800. So we can now look at this. Well, let's look first the probability of low depression. Well, how many have low depression? Look for a second, figure that out on your own. How many have low depression? Don't look at inside the chart, look in the margins. See, we're doing marginal probabilities. The margins on the sides and the bottom. Look on the margins. How many have low depression? Depression, low, 600 do. So we're going to throw in 600 there. So it's 600 divided by 800, which is also equal to 0.75. So we're going to throw in 0.75 under that. Sometimes you'll put it to the right of it. Sometimes you'll put it under it. I'm just going to put it under it for space. It's easier usually to put it to the right of it, but whatever one works for you. Some people will draw boxes. Now that we've got boxes drawn, we can just put it in the boxes. Okay, now about high depression. How many have high depression? Again, we're just looking at the margins. We're ignoring self-esteem. So we got 200 there that have high depression. So we plug that in, and we get 0.25, and we put that there. I want to point something out. If you add the total for low depression to the total for high depression, 600 and 200, you get the grand total, 800. Same if you added self-esteem, 300 plus 500, that equals 800. But one thing to add in here is our probability for the total is 1.00. If you add your probability, I'm just going to put some P's here so you see that we're looking at probabilities across the way. Our probability of having low depression is 0.75 and high depression is 0.25. You add those together, add 0.75 plus 0.25, you get 1.00. So that's something you can do to double check your work. If I gave you just 0.75 there, and I didn't even give you the 200 or the 0.25 for high, you'd automatically know though that it was 0.25 because again, 0.75 plus 0.25 equals 1. All right, let's look at the other two. Low self-esteem. How many have low self-esteem? You should have said 300 because 300 have low self-esteem. That is equal to 0.375. So we're going to put 0.375 there. How many have high self-esteem? I hope you already thought of 500. So we're plugging in 500 there. That is equal to 0.625. And now we can double check that math by adding 0.375 to 0.625, you add those together, you get 1.00. So it is again correct. And now we're going to go back and add another 0 here so we stay consistent. You're going to find we're going to end up adding another 0 even on top of that just to stay consistent, because we're going to go to 4 decimal places in the joint table. So we're currently doing the marginal probabilities. We did the marginal probabilities for depression and the marginal probabilities for self-esteem. We are now going to move on to the joint probabilities. I already mentioned the joint frequencies. Well, now you're going to be doing the joint probabilities. A joint probability is just the probability of the events occurring together. So again, we've got depression, we've got self-esteem. Joint probabilities are going to be in the table. It's going to be the probability of the intersection of events. That's another way to say it. It's the intersection of events. So probability of events occurring together, or the intersection. We write this as the probability, this is the way you're going to typically see it, the probability of A and B. Important word here, A and B. It is the probability of being both A and B. So if we're talking about, let's say, low self-esteem and low depression, it's the probability of having both low self-esteem and low depression. You may see it occasionally written like this. You may hear probability of A and B. This is the way right here you're going to see me write it. The probability of A and B is just the number of A and B, so the number at that intersection, divided by big N, which is again that grand total. So let's do some math now. First, I'm going to plug in some values that we already got. You remember this is equal to n, 800 is equal to n. So I plugged in those marginal probabilities, I plugged those back in. But now let's look at the joint probabilities. And again, these are in the cells, in the center. Let me draw some things here. So we've got our probabilities there. And now we are going to take and look at what's in the cells. But you'll recall the probability of A and B is equal to the number of A and B divided by our big N. So in all of these cases, we're going to be dividing by our big N, which is 800, our grand total, our N. So in all 4 cases, we are dividing by the total. But now we have to put in above it the number of A and B, or another way to say this is the joint frequency. So the number that are both A and B. So in this case, the number that are both low depression and low self-esteem. So where's low depression? It's there. Where's low self-esteem? It's there. So what do we get for a number there? I hope looking at it, you have decided that we are going to use 110, because 110 is the number of low self-esteem and low depression. So we plug that in, and we get, what is that, 0.1375, I think? So we get 0.1375. And we put that in here, 0.1375. How about high depression and low self-esteem? So now we're doing high depression, but we're sticking with low self-esteem here. So what is our number there? Number of high depression and low self-esteem? I hope you went with 190. 190 divided by 800 is 0.2375. Now you can double check your math actually here. Because if you add 0.1375 to 0.2375, you'll actually get 0.375. We're going to add another 0 on there just because these are 4-digit here. So we're adding another digit. But 0.1375 plus 0.2375, you add those together and you're going to get 0.3750. So adding this to this gives you this. Let's look now at low depression and high self-esteem. What's the number here? Well, I hope you said 490. And what do we get here? This is something like 0.6125. Yeah, 0.6125. Now, if you add, we can double check this as well. If you add 0.1375 here to 0.6125, you'll get 0.7500. And that is the case. And before we even do the math on this last one, we could check it out. Because we know if we add this 0.6125 to whatever we get here, we will get 0.6250. So we could just take 0.6250 and subtract 0.6125 and get 0.0125 there. But let's actually do the math. We plug in the value 10 divided by 80, and that is equal to 0.0125. It works out. We could have done it this way as well. We could have taken 0.250 here and subtracted 0.2375. In that case, we also get 0.0125. And if you had all 4 of these together in the center, you'll get 1.00. So there's lots of different ways to get it. I think the next slide has all those values just cleaned up. So here's all those values cleaned up. And again, I'm now going to write on it more. This plus this equals this. This plus this equals this. This, the 0.75 plus 0.25 equals there. This plus this equals this. If we took and went downwards, 0.1375 plus 0.23 equals that. And finally, 0.6125 plus 0.0125 equals 0.6250. So you can find out, if you're just given a few scores, a few numbers in here, you can find out all of the rest. You don't have to do all of the computations, but I recommend doing them just to double check your work. But this is the full, what is referred to as a joint probability table. If I asked you for a joint frequency table, it's what was on the last few slides before I wrote on them. If I asked for a joint probability table, it is this right here. You can write both of them together in the same table. So if I'm asking for both a joint probability and a joint frequency table, you can put them together in the same table like I have been writing on the previous few slides. Let's look at the last of these from Learning Objective 4, which is how to calculate conditional probability. Conditional probability is basically going to be the next step. So we looked at the joint probability. Well, we first looked at the marginal probabilities, which are simple. Then we looked at the joint probability, the probability of 2 events occurring together, the intersection. Next, we're going to look at the probability, conditional probability, which is the probability of an event given that another event has occurred, or given that another event is occurring, that type of thing. It is going to, instead of being straight up, it's going to now be a ratio of joint and marginal probabilities. So you need to, or a ratio of joint and marginal frequencies as well. You can calculate it either way to get the same thing. But we are going to take a ratio of joint probability over marginal probability. And you can do the same for frequencies. But let's look at that. So the probability, and this is how it's going to be written. This is the way you're going to say it. And the way we would say this is the probability of A given B. Now, one of the interesting things before when we were talking about joint probabilities. With joint probabilities, we've got the probability of A and B. We can actually change that around to the probability of B and A, and it does not change anything. Which one we say first doesn't matter when we're talking about a joint probability. These two things are equal to each other. They're the same thing. Probability of A and B is exactly the same as the probability of B and A, because it's just that intersection of events. However, conditional probabilities, the order does matter, because when we talk about this, it's the way we're going to factor this out, and we'll look at it with the probability formula, which is the one on the right. It's always going to be the probability of A and B, or of the two events, this event and this event. So we've got, when we're doing the probability of A given B, it's going to be the probability of the first event and the second event. We could instead say the probability of B and A, and that part of it is the same thing. That part of it doesn't change. But that's what goes in the numerator. What goes in the denominator, though, is what comes after the given. It's always what's after the given. So it's the last letter. So that's why the order matters, because if you change this order and you did probability of, instead of A given B, you did probability of B given A, it would change the denominator from probability of B to the probability of A. So always put what's in the denominator, or what comes after the conditional, after the given, in the denominator. And you can do this with both number, so you can do it with frequencies, or you can do it with probabilities. Let's look at some examples of that. So first, and we're going to look at the same example twice, but first we're going to look at with frequencies. So we're looking for the probability of low depression given low self-esteem. So, as I said before, the first thing is the number for the intersection, the joint frequency. So the number, low depression, and low self-esteem. Do you recall what that was? Low depression, low self-esteem, we've got 110. So it is equal to 110 divided by the probability of the given variable, the marginal probability of the given variable. So we're doing low depression given low self-esteem. So we are now going to look at low self-esteem's marginal probability or marginal frequency of 300. So what we're basically saying here, and the variable here is equal to 0.3667. It's actually 3.66 repeating, but 0.3667 is the probability here. But the important thing here is what are we doing? We are saying, okay, given that the person has low self-esteem. So now because we're saying low self-esteem, the given, what's after the given, you can talk about this in the first sense. Given that they have low self-esteem, so all we are concerned with is low self-esteem. Since we've made it a given that they have low self-esteem, all that we are concerned with, all that we care about is low self-esteem, because we've already said given they have low self-esteem. Now, given they have low self-esteem, we've brought our n down to 300, because we're only including those with low self-esteem, which is why our n of 300 ends up here on the bottom. So given they have low self-esteem, we've only got 300 people left in our variable. Now we're trying to see the probability of low depression and low self-esteem, which is that 110, as a proportion of 300. And that's what that 0.3667 is. We can do the same thing with probabilities, though, because again, probability, we're doing same low depression and given low self-esteem. Well, now it's the probability of low depression and low self-esteem. But again, like I said, we're only interested in low self-esteem because that's our given. So our low depression and low self-esteem is 0.1375 and our total low self-esteem is 0.375, which comes out to that same 0.3667. Same value, same answer, same everything, and it comes out that way. So let's just throw another example out there, just throw it out there. What about if I said, what's the probability that someone has high depression and high self-esteem given that they've got high depression? So probability of high, so I already basically said it, but the probability of high depression given that they've got high self-esteem. I think I said that wrong. So let me erase that because I said it the other way before. What is the probability? We'll just look at that. Probability of high self-esteem given they've got high depression. So I gave the given as high depression. What's the probability someone has high self-esteem given they've got high depression? So in this case, we're only looking at, because we're given high depression, we're only looking at high depression. So what's going to be in the denominator is the total for high depression. The total for high depression is 200. What is the total for high self-esteem and high depression? That's 10. 10 divided by 200 is 0.05. So that's another example. In class, I'll go over more examples. Next thing we're going to look at is the union of events. So the last thing we looked at was the intersection of events. Let's look now at the union of events. We'll come back and look at the intersection of events again later, but right now we're going to talk about the union of events. The union of events is the probability of event A or event B. So the previous one we looked at was event A and event B. Well, when we're looking at the union of events, we're looking at A or B. So when we look at this, the probability of A or B is going to be equal to the probability of A, the simple probability of A, plus the simple probability of B, minus the joint probability of A and B. Why do we need to subtract this A and B? Take a minute to think about why do we need to subtract the A and B. So it's pretty obvious, like if we're seeing A or B. So let's say, what's the probability of drawing a heart or a 10? What's the probability of drawing a heart or a 10 from the deck? Or my example from earlier, what's the probability of rolling a even or a low number? An even or a low number. Well, it's pretty obvious that if we're talking about even or low, we've got to concern ourselves with getting the probability of getting an even and getting the probability of getting a low, because both of those would meet our rule. If we're talking about, well, what's the probability of getting an even or a low? Well, even, we've got 2, 4, and 6. Low, we've got 1, 2, and 3. So all of those would count as successes. If we're looking where our probability of drawing or rolling an even or a low, if you roll a 1, a 2, a 3, if you roll a 2, a 4, a 6, all of those count as successes. So that's what we're looking for, the probability of rolling that. However, why do we subtract the probability of A and B? I'll do a graphical representation, but let's even look at it over here in my example. In even, we've got 2, 4, and 6. In low, we've got 1, 2, and 3. What have we done with 2? If we look at let's say we did the probability of even which is, I got enough space, is equal to 3 out of 6. The probability of low is equal to 3 out of 6. If we just did the probability of even plus the probability of low, we would get 6 out of 6. If we just did, let me put it, maybe, I think I'll have room here. If we did the probability of even plus the probability of low, it would be 3 out of 6 plus 3 out of 6, which would equal 6 out of 6. However, which would equal 1. There's not a full 1 chance. There's not a 100% chance of rolling an even or a low because we're missing the 5. And we did something with 2 specifically. With 2, we counted it twice. We counted it once in here, and we counted it once in here. So by subtracting the probability of A and B, so in this case, the probability of even and low is equal to, this is in case all the overlap, is equal to 1 over 6, because there's 2 is in both of them. So then if we subtracted down here, if we then subtracted, we did probability of even plus probability of low minus the probability of even and low, we would do 3/6 plus 3/6 minus 1/6, and we'd be left with 5/6, which if you look at it, we've got 1, 2, 3, 4, and 6. That's 5 cases out of 6. So why do we do that? Why do we need to subtract A and B? Because otherwise it would be counted twice. We are counting it in the A's and we're counting it in the B's. We're counting it twice. Or in our example, we would have 4 and 6 and 2, and we would have 1 and 2 and 3. We'd be counting 2 twice. Let's look at another example of that. What's the probability of getting a heart or a king? So the probability of a heart or a king is going to be equal to the probability of getting a heart plus the probability of getting a king minus the probability of getting a heart and a king, because if there's overlap, we don't want to count them twice. Well, the probability of getting a heart is 13 out of 52, because there are 13 hearts. The probability of getting a king is 4 out of 52. However, there is the king of hearts, so we have to subtract that king of hearts. So let's subtract 1 out of 52, and we are left with 16 out of 52, which, if I look that up, that gets us 0.31. So that's just another example there. And again, otherwise we would have counted the king of hearts twice. We would have counted it once there and once there. So we subtract it here to make sure we've only counted it once. Let's talk about mutually exclusive again. So we're going back to mutually exclusive. If you recall, we said before, mutually exclusive is where two events cannot occur simultaneously. If they cannot occur simultaneously, then they are mutually exclusive. So again, things like, looking at it here, like hearts and black cards, they're mutually exclusive, meaning there is no instances where you have both a heart and a black card. So if they're mutually exclusive, the probability of A and B equals 0. Because there are no hearts that are also black cards, all hearts are red cards, all black cards are spades or clubs, there are no hearts that are black cards, then the probability of A and B, the probability of getting a heart and a black card, is 0. You cannot draw one card out of the deck and get both a heart and a black card. Which comes back to the addition rule, but now we're going to talk about the addition rule with mutually exclusive events. So the addition rule with mutually exclusive events just says that we can eliminate the probability of A and B. So again, let's look at it. What's the probability of drawing a heart or a spade? So normally, the probability would be heart or spade would be equal to the probability of a heart plus the probability of a spade minus the probability of a heart and a spade. Probability of a heart is 13 out of 52. Probability of spade is a 13 out of 52. The probability of a heart and a spade is 0 out of 52. So because it's 0, we can just eliminate, when events are mutually exclusive, we can just eliminate that from it. And when mutually exclusive, the probability of A or B is just equal to the probability of A plus the probability of B, if they're mutually exclusive. And in this case, we get 26 out of 52, or 0.50. So next we're going to talk about the multiplication rule. And you notice the multiplication rule is similar to something it's actually the same as something we've already talked about. And that is the probability of A and B. So we've already talked about the probability of A and B. I actually used the term intersection when I talked about it. But now we're going to look at it in a context that is different than just when we're looking at it as joint probability. Sometimes you can do it simple, like as a joint probability, but sometimes it actually takes a little bit more. So we're going to use the multiplication rule to look at it a little bit deeper, and we're going to look at it with and without replacement, so that's another term we'll be adding. So the multiplication rule for this is going to be the probability of A and B will be equal to the probability of A times the probability of B given A. And it will also be equal to the probability of B times the probability of A given B. So we can look at that. It's a little bit more difficult than just getting our joint probability, but because we have to have a simple probability and we have to have a conditional probability. So what is the point of this being harder? Why do we have to add in this extra layer of complexity? Well, now we're going to talk about a term about without replacement. And in a few slides, I'll talk about it more. But basically, now we're not talking about one event, we're talking about multiple events. So before, when we talked about the joint probability, we were talking about a joint probability of having low depression and low self-esteem both at the same time. We were talking about essentially two different things, but occurring at the same time. Now we're going to start talking about, well, what's the probability of getting two different things in succession? So, like, what is the probability of drawing a heart and then a red card in succession? So that's where we're going to now have probability of heart and red. But we're talking about drawing it as two cards in a row, not as one single card. Before we talked about, well, what's the probability of getting a heart and a 10 on one draw? That was the joint probability we're looking at. Now we're looking at A and B, probability of A and B, but now we're looking at it in a series of events. So what's the probability of getting a heart and a red card on two different draws? And we're using this special term here without replacement, meaning we don't put the first card back. So it's going to be equal to the probability of getting a heart times the probability of getting a red card given we got a heart on the first draw. So what is the probability of getting a heart here? Well, there are 13, so it's 13 out of 52. What's the probability then of, we're going to multiply that by the probability of getting a red card given we got a heart on the first draw, and we did not put that heart back. That's important. Without replacement means we did not put it back. It means, first of all, there's only 51 cards left in the deck because we didn't put the first card back. So our total N went down because we took one out and didn't put it back. But then how many red cards are there? Well, we've already taken one out. Normally there's 26, but we drew one here. So given that we drew a heart on the first one, we drew a heart, we didn't put it back. So now there are only 25 red cards left. And then you'd multiply those out. It's 0.25 times, what is 25 divided by 51? It's 0.4902, so we get 0.51. So the probability of getting a heart and then getting a red card is 0.51. Oh, did not do that right. Oh, I did it wrong. It's 0.25, so ignore that. I was going to say that should be the wrong number. Let's erase that and actually get it. So it is going to be 0.25 times 0.4902, and that gets us 0.12. So our final answer there is actually 0.12. There's a 0.12 probability of getting a heart and then a red card given we drew a heart with the first card and did not put it back. That's without replacement. So when we talk about independent events are when the occurrence of one event does not affect the occurrence of another event. And that's important here when we're looking at this, when we're looking at what's going on with these intersections of events. Because if the events don't affect each other, then the probability of A given B is going to be equal to the probability of A. If B does not affect A at all, it doesn't matter if B already occurred or not, A is going to have the same probability because they're independent. One event does not affect another event. Let's say, for instance, and I'm going to use those without replacement and with replacement that we're going to talk about on just the next slide, a couple slides from now. But let's say I was asking about the probability of drawing a heart given we've already drawn a red card, but we put that red card back in. Does it matter that we already drew a red card? No, because we put that card back in before we drew the second card. If we kept it out, then it would matter, but they're independent because I put the card back in. I could draw 50 cards out of a deck. If I put them all back in, the next draw, it's still going to be out of 52 cards. And probability of B given A equals probability of B. I point these out because I'm going to ask at one point on the exam if two events are independent, and I'm going to give you the probability of A given B and the probability of A, and you should be able to calculate to see if they're independent or not. Because if the probability of A given B equals the probability of A, you might even have to calculate out the conditionals here. But if the probability of A given B equals the probability of A, then they're independent. You also have to check to see that the probability of B given A is equal to the probability of B. We'll talk about that again later, though. Let's look at some independent events. Example here, flipping a fair coin. If you flip a coin, the probability that it comes up heads does not depend on any outcome that's occurred on a previous toss. It's going to be 0.5 no matter what you do. You can flip that coin 1,000 times. If it came up heads, let's say you flipped the coin 10 times, it came up heads 9 times in a row. What's the probability you're going to get heads on the next row? 50%. It doesn't matter what's already happened. That's actually what's referred to as the gambler's fallacy, where you previous events you think have an effect on later events when they don't. Our minds like to attribute cause or dependence to independent events, and that's what the gambler's fallacy is. So don't fall into that. Just remember, if the events are independent, then that probability is not going to change. So when you say something like a certain number is due at the craps table, something like that, or a certain card is due to come up, or a certain die roll is due, a certain flip of the coin is due, that's a fallacy. Nothing is due. The probabilities are still the same every single time. So that gets us to that, what I was saying, with and without replacement. So sampling with and without replacement. First off, with replacement means you reset the sample space between each attempt. So if we're talking about decks of cards, you draw out a card, then you put it back in the deck and shuffle the deck again. Sometimes with replacement is default. If we're talking about flipping a coin or rolling a die, it's always with replacement. Because when you roll a die, you don't take off one of the faces of the die. Every time is going to be independent, so every time is with replacement. Flipping a coin, the same thing. You can't take off heads after you've flipped heads. So every time you flip, it's with replacement and it's independent. Without replacement, though, is where the outcome is not replaced prior to the next selection, thus the events are dependent. So an example here would be like with playing cards. If you didn't put the card back in after you drew it out, now on your subsequent draws, it's going to change the number. Let's say we were drawing beads out of a bag and we had 5 red beads and 5 green beads. If we do with replacement, we draw the first one and we get a red bead. What's our probability with replacement of drawing a red bead on the next one? It's still 0.5. It's still half because we've got 5 and 5. So with replacement, it's like that. But what about without replacement? Let's say I draw a red one out. What's my probability of drawing a red one out on the next draw? Well, now it's only 4 out of 9 because there's only 4 red beads left and there's only 9 beads total. So without replacement, if we don't put it back, is dependent. It's not going to change, or the probabilities are going to change from draw to draw. With replacement, they're independent. The probabilities are not going to change from draw to draw. Which gets us back to the multiplication rule, the intersection of events without replacement and with replacement. If we are doing with replacement specifically, then since the probability of A and given A and B, since when they're independent, the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B, then we can just change these. We can change these to just this is the probability of B, and this is the probability of A. And we end up with just the probability of A and B is just the probability of A times the probability of B when they are independent. That's very important. When they are independent, probability of A and B is just the probability of A times the probability of B. So for example there, let's actually look at it on the next slide. What's the probability of drawing a heart and then a red card with replacement? So before we did the same example without replacement, let's do it with replacement now. So probability of A and B is normally probability of A times the probability of B given A, but since we are doing independent with replacement, so they're independent, since they are independent, the probability of B given A is equal to the probability of B. Our formula just becomes the probability of A times the probability of B. And in this case, the probability of A, and we can change these. Let me just use the eraser a whole bunch. too much. I've been using A's and B's when I should have been using so the probability of heart and red. So it's going to be the probability of a heart and then the probability of a red given we've drawn a heart. But since the probability of red given we've drawn a heart is just equal to the probability of red, we're going to do the probability of heart times the probability of red. In this case, a heart is 13 out of 52. A red is 26 out of 52. It's 0.25 times 0.5, which is equal to 0.125. It is actually very similar to the answer we got before. The answer we got before was 0.122 for without replacement. With replacement is 0.125. They're very close, but they are different. If we rounded this one, we'd be rounding it to 0.13. As I said, 0.122 and 0.125, they're close, but they're different. And then just kind of as a last topic there when we're talking about with and without replacement, an important thing is here is when you're sampling without replacement from a super large population, you can treat any consecutive events as independent, even if you're doing it without replacement. What do I mean by that? Well, let's assume a university has 30,000 students, really big university. 15,000 are male, 15,000 are female. Let's even assume it's exactly equal, 15,000 male, 15,000 female. If you randomly select two students, what's the probability that both are male? Again, if you're technically doing that, you're doing it without replacement because you've selected two. You've selected one, you can't select that one again as your second one. So you select two different students. You're doing it without replacement. You selected the first one and you did the second one without replacement. Technically, you'd have to do 15,000 divided by 30,000 times 14,999 divided by 29,999. But if you do that, if you do the math for this, you're going to get 0.25. If you do the math for it, if you treated them as independent, you get 0.25. 15,000 divided by 30,000 times 15,000 divided by 30,000, which is also 1/2 times 1/2, it equals 1/4 or 0.25. You get the same answer. Again, it's just the multiplication rule for independent events. So with sufficiently large sample sizes, you can treat them as independent. It's just kind of a little aside there. Let's get to learning objective 7. And this is a fun one. Now we're going to talk about the special case. This is a special case of probability, the probability of at least one. So we've been talking prior to this point, what's the probability of getting an exact thing? What's the probability of drawing a heart? What's the probability of drawing a red card? Well, what if we said, what's the probability of drawing at least one ace if we draw 3 cards? And so we would have, or let's say, what's the probability of drawing at least one red card if we draw 3 cards? So you draw 3 cards, at least one red card. Well, the probability of the first card, we've got the probability of a red card. This is we're going to do with replacement. So it's going to be the probability of a red card times the probability of a red card times the probability of a red card. Well, there you get 26 divided by 52, or 0.5 times 0.5 times 0.5. We've got a problem here, though, because what you end up getting here is equal to 0.125, and your probability of getting at least one red card is not 0.125. What we actually calculated here is the probability of getting 3 red cards, or the probability of getting a red and a red and a red. We calculated, instead of the probability of getting at least one red card, we calculated the probability of getting 3 red cards. Why did I use that as an example first? Because every year when I give a question like this on the exam, somebody uses this formula for probability of at least one instead of the formula I'm going to talk about. So I want to first talk about what you shouldn't do. And that is use the probability of red and red and red, because what you're really calculating there is the probability of getting 3 red cards, not the probability of getting at least 1 red card. Because you could, let's just look at the different ways you could draw. You could draw a red card, then a red card, then a red card. That's the one we just looked at. Or you could draw a red card, then a black card, then a red card. Or a red, then a black, then a black. And we could even looking at other cases. Let's do black first, black, red, red, black, red, black, 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 red, and black, black, black. I think I'm missing one, but maybe I'm not. Nope, I am definitely missing one. There should be 8, and I've only got 7. So, but the point here, oh, I'm missing red, red, black. So now we've got 8. Those are the 8 different possible outcomes. We could count these up. We could do the math, and we'll do this actually in a future one where we're doing a little bit of different. We can see that in cases where we got at least 1 red card, or in all of these, we got 3 red cards here. 3 here, 2 here, 2 here, 1 here. We got 2 here, we got 1 here, we got 1 here, but here we got 0. So we can even see that our probability of drawing at least 1 red card is 7 out of 8, because 7 out of 8 instances we get a red card. But there's actually an easier way to calculate this rather than figuring out all possible outcomes, because like I said there, I missed an outcome. If I miss an outcome, that messes everything up. So instead, we're going to do this special case of the probability of at least 1. That is, first off, we need to know this thing that we were talking about before, and that is if we have mutually exclusive exhaustive categories, they form a partition, then they sum up to 1. So if we look at, let's say we talked about the probability of getting, in this case, we've got 3 draws. The probability of getting 0 red cards, the probability of getting 1 red card, the probability of getting 2 red cards, and the probability of getting 3 red cards. And if we had 4, that's what the ... here is for. If we had 4 draws, it'd be the probability of getting 4 red cards. If it was 5 draws, the probability of getting 5 red cards. However many draws we are, that's the probabilities we're looking at, and whatever it is we're looking for. In this case, we're getting at least 1 red card. So it's important to note that if you add all of those probabilities together, you get 1. That's important because now we can just use simple math to figure out what the probability of that box is. How can we do it? We need to eliminate what's outside of that box on the other side of the equal sign. What's outside of the box that we've got here? So we've got this box here. Let's do simple math, simple algebra. We want to isolate probability of 1 plus probability of 2 plus probability of 3. We know that, again, let's just write it here. Probability of 0 plus probability of 1 plus probability of 2 plus probability of 3 equals 1. We want to isolate this and see what it equals. Well, what do we have to do? We have to subtract probability of 0 from each side. And we are left with, because what's in the box is the probability of at least 1, because if you get 1, you've got at least 1. If you get 2, you've got at least 1. If you've got 3, you've got at least 1. What we are left with is that the probability of at least 1 equals 1 minus the probability of 0. And we can factor out, without even having to do all this over here, we can figure out the probability of 0 very easily. So what is the probability of getting 0 red? This is also known as the probability of getting not red. So what is the probability of getting not red on 3 draws? On 3 draws. Well, the probability of getting not red on 3 draws is going to be equal to the probability of not red and not red and not red. That means we drew 3 times, and on all 3 we did not get red, because anytime we would draw red, then we've hit the at least one side. So this is the probability of getting not red and not red and not red. Well, again, just like the probability of getting red is 0.5, the probability of getting not red is 0.5, because there's 26 black cards. So it's going to come out to 0.5 times 0.5 times 0.5, because just like up here, it's the probability of not red times the probability of not red times the probability of not red. So it's 0.5 times 0.5 times 0.5, which is equal to that 0.125 up above. But that isn't the probability of at least 1. The probability of at least 1 is going to be 1 minus that, because that was the probability of 0. Probability of 0 red is equal to that. So 1 minus 0.125, and we get 0.875. So the probability of getting at least 1 red card on 3 draws is 87.5%, 0.875. And I want to point out this. Let's say we did go back to this we've got here, where we had 8 instances, and only one of those was a case where you got no reds. The only one where we got no reds is this one. So in all other cases, the 7 of the 8 cases, there was 8 cases, 8 possible outcomes. In 7 of 8 outcomes, we got a red. Well, what's 7 divided by 8? 7 divided by 8 is 0.875. Same answer that we got there. Let's finish this up before we talk about the probability distributions with using both rules in the problem, using the or and the and. And I kind of did this in the last slide, looking at the probability of at least 1. But some problems require us to use both. So let's say we're flipping a coin 4 times. What's the probability of getting exactly 2 heads? So now we're into another interesting one. What's the probability of getting 2 heads? So we're not looking at 1 heads. We're not looking at 0 heads. We're not looking at 3 heads. We're not looking at 4 heads. We're only looking at the possibility or the probability of getting exactly, this exactly is a big word, exactly 2 heads. This is actually going to lead us to our first probability distribution we're going to talk about coming up next. But it leads us to it because the way we do that probability distribution that we'll talk about, the binomial distribution, is it's designed to calculate exactly so many outcomes. But first, before we get to that, let's look at it doing it the way where you're using both addition and multiplication, which makes it a little bit harder. First off, these are all of the outcomes that have exactly 2 heads. So in this case, we've got head, head, tail, tail, head, tail, head, tail, head, tail, tail, head, tail, head, head, tail, tail, head, tail, head, and tail, tail, head, head. These are all possible outcomes. So there are 6 outcomes that have 2 heads. There are no other outcomes that have 2 heads. Well, what we can do is we can first use the multiplication principle. That is, we can figure out what the probability of getting this is, this specific one right here. And what is it? Well, it's going to be the probability of getting a head and a head. Actually, probability of getting a head, and then a tail and a tail. So it's a head, head, tail, tail. Because flipping a coin doesn't worry about with and without replacement, we don't have to worry about that. So it just becomes the probability of getting a head times the probability of getting a head times the probability of getting a tail times the probability of getting a tail. Which, again, each of these is 0.5. So 0.5 times 0.5 times 0.5 times 0.5. So we get 0.0625. So the probability of getting this specific outcome right here is 0.0625. And interestingly enough, I'm going to flip slides. The probability of getting each and every one of those outcomes is the same. Because it doesn't matter if you flip a head or a tail, it's still 0.5. So all of those outcomes are specified outcomes. So all of those outcomes have 0.0625. So that's how you use multiplication in the rule. Now, where does addition come in? Well, if you add up the probability of each of those individual outcomes, so add up all of those 0.0625s, you get the probability of flipping two heads. That is our probability that we're looking for, that 0.3750. How does that make sense? Well, again, these are all of the different outcomes that could lead us to two heads. So if you take the probability of each of these individual outcomes, then add them all together, you get all of the total probability of getting two heads. We'll actually look at this a little bit more coming up on the next slide when we talk about the binomial distribution. So looking at that binomial distribution, which is learning objective 8, calculate the probability of a specified number of outcomes occurring during using the binomial probability distribution. You'll notice right there that it's talking about a specified number of outcomes. So it is any time where you have exactly two possible solutions or two possible outcomes on any given trial, on one trial. What do I mean by that? Well, obviously, like heads and tails, there's two outcomes. But how would we do it, let's say, with rolling a die or a deck of cards? Well, in that case, what we would be looking at is the event and its complement. So let's say we were trying to look at drawing hearts. We were trying to draw cards out of a deck, and we were trying to see what's the probability of drawing two hearts on 3 draws. Well, our one outcome is hearts. The other outcome is not hearts. So it's everything that is not hearts. So there's still only two possible outcomes, success on the trial or failure on the trial, even if it could be many different cards individually. But the probability stays the same regardless of what you draw out. You either draw a success, which would be a heart, or you draw a failure, which would be a not heart. And it's the whole point of the binomial distribution, though, is it's when you're looking for a specified number of outcomes. So when you're looking for a, I can get down here. So it's a specified number of outcomes. So let's say we're drawing some 3 times and we want 2 successes. So it's a specified number of successes on a given number of draws. On a given number of trials. It's a better way to say it. So it's a specified number of outcomes or successes on a given number of trials. Our formula that we're going to use is right here. And you'll notice something right away. This is where we're going a little bit more in depth, or there's a math symbol here that we haven't used before. And with the exception of this formula, we won't use it again in this class. And that is the factorial here. But let's look at that then. The factorial is going to be the product of all integers between 0 and x. What do I mean by that? I mean, if we had, let's say, 4 factorial, it's going to be equal to 4 times 3 times 2 times 1. So in that case, 4 factorial is equal to 24. 3 factorial is equal to 3 times 2 times 1. So it's equal to 6. 2 factorial is equal to 2 times 1. So it's equal to 2. 1 factorial, pretty evident, it's equal to 1. A special case, so we're going to do a special case here. 0 factorial. This is important because if you don't do this special case, it'll mess it up. 0 factorial is also equal to 1. 1 factorial is equal to 1 and 0 factorial is equal to 1. Now you can figure this out, any factorial. Let's say 5 factorial is 5 times 4 times 3 times 2 times 1. You can already tell that we're going to get into some big numbers because 5 factorial is 120. 6 factorial is, 720. So it gets really large numbers as you get up into bigger factorials. I'm telling you right now, for in here, we're never going to go over 4 factorial. So everything with factorial is actually on this slide. 4 factorial is 24, 3 factorial is 6, 2 factorial is 2, 1 factorial is 1, and 0 factorial is 1. Now there's a few more things going on with this formula that we're looking at here. So again, this is the probability of something. N is our number of trials, the number of trials, the specified number of trials that we talked about. R is our number of specified successes, our number of specified outcomes or successes. So that was our number of successes. Then P over here is the probability of a success, of a positive outcome, a success. Q, which is right here, is the probability of a negative outcome or the probability of a failure. So when we're talking about it, these are going to be complements of each other because the probability of a success, its complement is going to be the probability of a failure. And these two are going to add up to be 1. So that's everything that's in this formula. We'll look at it in just a second. We'll use a couple examples, but I just kind of want to get at that. So what did we look at on the previous slide? What is the probability of getting, flip a fair coin 4 times, what's the probability of getting exactly 2 heads? So the number of trials in that case is going to be 4. So N is going to be equal to 4. Our specified number of outcomes, R is going to be equal to 2 because we're looking at 2 outcomes. What's the probability of a success? Well, the probability of getting a heads is 0.5. What's the probability of a failure? Well, the probability of a tails is 0.5. So P is equal to 0.5. Q is equal to 0.5. And then we just need to plug this in. Let's actually plug these into this formula. So we've got N factorial, so 4 factorial, divided by R factorial, so 2 factorial, times N minus R factorial, so 4 minus 2 factorial. All of that times P, 0.5, to the R power. R again is 2, times Q, which is also 0.5, to the N minus R power. So to the 4 minus 2 power. Just put parentheses around that so you know that they're there. And then it'd just be a matter of figuring it out. So if we look at this, again, 4 factorial. Let me even erase what's over here. So 4 factorial is, I set it down here as 24. 24 divided by 2 factorial, which is 2, times 2 factorial, 4 minus 2, which is 2, 2 factorial times 2, so it's 2 times 2, or it's 24 divided by 4, we'll just look at that. We'll bring that down. 24 divided by 4 is 6. Then we'll look at 0.5 squared is 0.25. And 0.5 to the 4 minus 2 power, again 0.5 squared, is 0.25. 0.25 times 0.25 is 0.0625. So it's 6 times 0.0625, which is equal to the exact same thing we got on the previous slide, which was 0.3750. Because there were, just like on the previous slide, there were 6 instances of probability of 0.0625. Let's even expand on that a little bit more, what I mean by what's going on here and what's going on here. So what's going on this left side? That's where we got the 6. So on the left side, that's the number of outcomes that provide exactly that number of successes in the end trials. So you'll recall in our flipping coins ones, we had exactly 6 cases where we would flip 2 heads. You can rewind the video, go back to it, and see that we had exactly 6 cases where 2 heads was possible on 4 flips of the coins. That's why the one over here was 6 on the previous slide, because there was 6 outcomes that provided that many successes on 4 trials, 2 successes on 4 trials. On the right side here, that's the probability of any one specific outcome. The probability of a particular sequence of trial outcomes with X successes on N trials. What do I mean by that? Well, that's the probability for each of these individual 6 outcomes to happen. And if you rewind the video, the little lecture a little bit, you'll see that each of those individual outcomes had a 0.0625 chance of occurring. And if you multiply those two together, you get that 0.3750, because that is the probability of getting 2 heads on 4 flips. So the left side is the number of successes, the right side is the probability of each individual success. You multiply those together and you get the actual outcome. Let's look at another example. So another example, now let's say we want to flip 2 heads if you flip a coin 3 times. Not 4 times, 3 times. So let's plug all this in. So again, N in this case is 3. I'm just going to put 3's each of those places. R is still 2. P is still 0.5. And Q is still 0.5. When we plug that in, we get 3 factorial. If you'll recall from 3 factorial, it's 3 times 2 times 1, which is 6. 2 factorial is 2. 3 minus 2 is 1. 1 factorial is 1. 2 times 1 is 2. Then we're going to multiply that by 0.5 to the second power, which is 0.25. And we're going to multiply that by 0.5 to the first power, which is 0.5. And what we get is 3 times 0.25 times 5. Well, 0.25 times 5 is 0.125. 3 times 0.125 is actually equal to that same number we just got a minute ago, which was 0.3750. That is, the probability of getting exactly 2 heads on 3 flips is the exact same as the probability of getting exactly 2 heads on 4 flips. Just one of those interesting quirks of how it works with flipping it. But what do I mean by, well, what is this 3 here? Well, if we flip it 3 times, we can get heads, heads, tails as a success. We can get heads, tails, heads as a success, and tails, heads, heads as a success. In each of those 3 cases is the only cases where you can get exactly 2 heads. So there are 3 cases, 1, 2, 3 cases where we've got exactly 2 heads. How about this 0.125? Well, that's 0.5 times 0.5 times 0.5, because that is the probability of this exact outcome. You have a 0.5 chance of getting a heads, 0.5 chance of getting a heads, and 0.5 chance of getting a tails. You multiply them together, you get that 0.125. So if we did that through all three, you get the same thing as we got up here. So that's just another example of it. The last thing I want to talk about with the binomial distribution is why it's called a distribution. And why it's called a distribution is because it is all possible outcomes, if you look at it, for that specified number of trials, and you can put those into a distribution. What do I mean by that? I mean, let's say we had 10 trials where we flipped a coin 10 times. Well, you can put these into a distribution. This is the probability of getting exactly 0 heads on 10 flips. Exactly 1 heads, 2, 3, 4, all the way up. This is the exact probability of getting this number of heads on each of the flips. And you can put all these together and you've got now a distribution. So this is the last learning objective, which is compare and contrast the hypogeometric probability distribution, the Poisson probability distribution, the exponential probability distribution, and Bayes' theorem. So I'm going to say right now, just going to get this out of the way. You do not need to know how to calculate these. You do not need to know anything with these other than what the purpose of them is. I'm going to show you the formulas, but I'm not going to show you examples, and I'm not going to expect you to calculate it. It's not going to be on the homework. It's not going to be on the exam. It's not going to be for calculations on the exam. However, it might be on part A of the exam asking you about similarities and differences between these different distributions or specific things from them. So at least know what the distribution is for, what the differences between them are, and what they do. So this last learning objective, it goes through the last about 10 slides of the lecture. So I'm going to talk about those. So the first one of those is the hypogeometric probability distribution. And interestingly enough, the hypogeometric probability distribution is a lot like the binomial distribution. You'll recall that the binomial distribution, we just talked about it, it's looking for a specific number of successes on a specific number of trials. The issue here is that the trials have to be independent for the binomial distribution. The trials have to be independent. So one trial to another, it has to be reset. When you're doing something like flipping a coin, that's not a big deal. They're going to be independent by default. Rolling a die, independent by default. How about drawing a card out of a deck of cards? Well, in that case, to keep it independent, you have to reset the deck every time you draw a card out. You can't draw 2 cards out and use the binomial distribution. You can't draw 2 cards at once and use the binomial, because by drawing 2 cards at once, you're technically drawing the second card you're drawing of those 2 is dependent on what you drew on the first one, even if you're drawing them at the same time, because you don't have a chance to redraw that first card as your second card, as your second trial. So because of that, it's pretty fixed. And there's a lot of real world situations where it doesn't work. So instead we use the hypogeometric distribution, and in this case, the trials are not independent because the probability of success will change from trial to trial. And our formula for it is what you see here, and this is not as easy as it looks. It might look kind of easy, but this right here, R over X, is not equal to R divided by X. It is R selected from X. And there's some things you have to do with basically going into those factorials, but you have to do factorials and you have to do subtractions from factorials and you have to, it's a very complex problem. If I had you guys do this as a calculation, this problem would be the hardest thing you would do calculation-wise, math-wise, all semester long. That's why we're not doing it. But again, this is basically a probability distribution that's entire point is when you're looking for a specified number of outcomes on a specified number of trials, but the trials are not independent. The next distribution is the Poisson probability distribution. And the Poisson probability distribution is basically looking at estimating the number of occurrences. So we're still on number of occurrences, but now instead of number of occurrences on a specific number of trials, it's number of occurrences over a specified interval of time or space. What do I mean by that? I mean something, or what is it, would be an example there? An example here would be like the number of knot holes on 14 feet of pine board, or the number of vehicles arriving at a toll booth in 1 hour. So this is specified space, this is specified time. So this is when you would use it. When we're talking about the Poisson probability distribution, it's interesting that the probability of occurrence is the same for any two intervals of equal length. So again, they have to be the same. The probability can't change, and the occurrence or non-occurrence of any interval has to be independent of occurrences or non-occurrences in any other interval. So technically, when we looked at the toll booth, it wouldn't fit 100% in Poisson if we were looking at it in a 24-hour period. But let's say we were looking at it at a specific period of time, and we know that, let's say, between 2 and 3 p.m. every day, a specified number of vehicles arrive in 1 hour. The next day between 2 and 3 p.m., or on any given day between 2 and 3 p.m., how many should we expect? So then it's the probability of occurrence is the same for any two intervals of equal length. As long as, again, we've got to control for like weekends and things like that. But let's say on every Tuesday, we get 10 vehicles at the toll booth between noon and 12:30. Well, how many should we expect? We get that on average. How many should we expect on the next Tuesday to get between noon and 12:30? And we would go off from that, and that's how this distribution would work. The formula for this distribution is U, where U is the mean number of occurrences in an interval. So in my example, let's say we had 10 vehicles on average during that period of time. So U there, or mean, it's not U, it's the mean is technically what that is. The mean here would be 10. And that's to the x power, whereas that's the number of occurrences in an interval, times E. E is a constant here, and that's to the negative mean power. So again, a little bit complex here, then divided by the number of occurrences in an interval that we're looking for. So we're trying to see, let's say we know the mean is 10, we're trying to see, well, what's the probability that 5 vehicles will go through in this time? That's how we would use this formula. And since there's no stated upper limit here of occurrences, the probability function is applicable for any number. We could say, okay, what's the probability that 10 vehicles come through? What's the probability of 20 vehicles come through? What's the probability of 1,000,000 vehicles coming through? Well, the probability of 1,000,000 vehicles coming through in that time is basically 0. Theoretically, something could happen and 1,000,000 vehicles could fly through in that time, but it's impractical. Even 1,000 vehicles in that time is basically a 0 probability. But at some point the probabilities are going to become negligible. But the point is there is no upper limit. This is going to shift us to the probability of continuous variables. So we've been looking at fixed numbers, discontinuous variables to this point in time. What's the probability we get two heads on 4 flips? What's the probability we draw 2 hearts out of a deck on 2 draws where we draw those 2 cards at the same time? That's the hypogeometric. What's the probability that 10 cars come through the toll booth between 12 and 12:30? So those are all discontinuous variables because you can't have part of a variable. Well, now we're going to change it up a little bit, and with this last distribution here, we're going to talk about what happens when we have a continuous variable. And the thing is, when we're doing a continuous variable, we're looking at that area under the curve, like when we did with z-scores. We're looking at an area under a curve for a range of scores rather than a specific score. So let's say we were talking about intervals of time, we'd be looking at a range of time as it pertained, and what is the probability that something falls into that range of time. So we can convert x-scores to z-scores, use the standard normal distribution, and use the z-score tables given proportions for area under the curve using probability. Again, you guys aren't going to have to do that, but that is something you can do. Example here, assume test scores are normally distributed with a mean of 10 and a standard deviation of 2. What's the probability of getting a score of 13 or higher? So this here, maybe you can only get whole numbers, but maybe you can get parts of numbers. So if you can get parts of numbers, then we've got a continuous variable. We get the z-score for 13, we get the z-score for 10. Example here, assume test scores are normally distributed with a mean of 10 and a standard deviation of 2. What's the probability of getting a score of 13 or higher? So this here, maybe you can only get whole numbers, but maybe you can get parts of numbers. So if you can get parts of numbers, then we've got a continuous variable. We get the z-score for 13, we get the z-score for 10. Sorry, my slide skipped ahead on me, and there's no way to go back unless I re-record the entire slide, so I'll just finish what I was saying on this slide, and that is you get the z-score for a x value of 13 with a mean of 10 and a standard deviation of 2, you get the z-score of 1.5, and you find the probability on the z-score tables at and below that point, and the z-score, the area under the curve at and below a, or between, we're now looking at not at and below, but at and above. At and above, the area under the curve is 0.0668. So there's a 668 probability of getting 13 or higher on that test. Okay, now we are to that final probability distribution, which is the exponential probability distribution. And it is very similar to the Poisson distribution, except whereas the Poisson distribution was looking at the number of occurrences over a specified interval of time or space, the exponential is looking at the specified time or space for a number of occurrences. So it can be used to describe like the time required to complete a questionnaire or the distance between major defects in a highway. So the exponential distribution, the mean and standard deviation are equal, and it's skewed to the right with a skewness measure of 2. And we're going to look at 2 different probability functions, 2 different formulas for this, for the exponential. One is for a specified value, and the specified value is good when you're looking at just one thing. Like again, we were looking at going back to that, like the time required to take a questionnaire. So if we're looking at exactly 1 hour, well, we can look at this function. And it's 1 divided by the mean to the e, or times e to the x minus, it's the mean minus the x minus the mean. So yeah, you can see here, again, I'm not going into this too much. I could spend time explaining, and again, like I said before, this E is a constant, but we're not going to really deal with that because you guys aren't going to be calculating it. And this function works okay, but like I said, when you're talking about intervals, when you're talking about a continuous variable, what should be more important is cumulative properties. So the cumulative property, the cumulative is everything at and below that point, is going to be 1 minus e, which again is 2.71828, to the negative x, where x is the specific value of x, divided by the mean. So you can see here, this is a little bit easier of a formula, but this one's used more often than just the density function. Again, you guys don't have to calculate it, I'm just showing them to you. What's on this slide is important though. What's on this slide is the difference between the Poisson and the exponential. I already told you the difference between the hypogeometric and the binomial, because those are testing the same thing in different ways. Well, the Poisson and exponential are testing the same thing in different ways. The Poisson is looking at the number of occurrences per interval. So it's looking at x per interval of space or time. The exponential is doing the opposite of that. It's looking at the interval between occurrences. So the Poisson is looking at how many instances occur in an interval, number of x's. The exponential is looking at the distance between x's, the length of interval between occurrences. And that can be the same thing as the Poisson. It can be an interval of time or space. Then we get to the last distribution, and I'm not going to spend too much time on this distribution. If we spent multiple weeks on probability, this would be like 10 slides just for the Bayes theorem. But the Bayes theorem is basically, what it does is it's all about looking at how probabilities change when you get new information. So we will begin with a prior probability. This is basically, okay, on Tuesdays, we expect 10 cars to go through the toll booth between 12 and 12:30. That's the prior probability. And we would factor out the probability there. We'd get the probability of 10 vehicles going through, and it's based on that prior information. So we would use those distributions, get that probability. We've got our prior probability. That's the prior information. Then new information comes along. Let's say they're going to close the highway, or they're going to they're going to close another highway, which is going to cause more traffic on the highway with the toll booth. So new information comes along. What we do is we take that new information and get new probabilities, which are called posterior probabilities. And how do we do that? We do that with Bayes' theorem. As I already said, I'm not going to even go into the details of it because there isn't really a formula for it. It's about 10 slides of do this, then do this, then do this, then do this, then do this. We're not going to do that. Just know that the Bayes theorem, the whole point of the Bayes theorem, is to get posterior probabilities or new probabilities based on using new information and prior probabilities. We don't just take the new information, we take the new information, apply it to the prior probabilities, and that gets us the posterior probabilities. And this application here and here is through the application of the Bayes theorem. Okay, that was a very long lecture. I am sorry about that, but we looked at things like defining probability. So we define probability, the basics of probability, some of the early things like defining the sample space in events. So those are things that you should really expect on a part A of an exam, is being able to explain those. Then defining the complement of an event and the probabilities of an event and its complement. The not the probabilities, the properties. There was those three properties of an event and its complement. After that, we got into the calculation side. So calculating marginal, joint, and conditional probabilities. Calculating the union of events, both using the addition rule with and without mutually exclusive events. Then we calculated the intersection of events with and without replacements. Then we calculated the probability of at least one. Then we used binomial to calculate the probability of a specified number of outcomes occurring using the binomial probability distribution. And finally finished up looking at these other probability distributions like hypogeometric, Poisson, exponential, those probability distributions, and finished up with Bayes' theorem. Thanks, come on back.